Hello everyone, this chapter will give you an introduction of the basics of computer networking. So we'll talk about some basic concepts, some terms related to the internet, and also the network that we have been using today. So we are going to use cloud computing as an example here. So the simple internet communications in a very simple presentation is like this. So when you use your phone or computer and then you try to connect to a website, so what you are going to do is you're basically connecting your phone to the internet, and then the internet will get something like, for example, an HTML file or an image or a movie from a web server. And the web server program will respond. And then everything that we have in between is what we call the internet. So one thing we would like to look at is on what we call the address. So each device on the internet will be given an address or would have an address. For example, like in this case, like the computer, the client computer tablet here is having a host IP address. For example, it's 1.2.3.4, and the host IP address is 5.6.7.8. So this is the mechanism of how devices can be able to find each other on the internet. So in the IP4, so IP, there are different versions for IP addresses. So in the IP version 4 address, each address is basically having 32 bits. And then we use what we call a dotted decimal notation, where we group the 32-bit IP addresses into 4 8-bit segments like this. So in total there are 32 bits. And then we convert each segment from binary to decimal, right, like this. So in this case, if your 32 bits are like this, then your IP address will be 1.2.3.4. The core of the internet basically is formed by a lot of internet service providers. And so they will connect to each other, and then besides, there are also some other different users of this internet. For example, like it can be universities, it can be companies, it can be some cloud service providers, it can be some personal users, and they are all connected to their respective ISP, right? Their internet service provider. For example, if you are using your network at home, then you'll be connected. You will connect to the internet basically through your service provider like HKBN or like Hong Kong Broadband or PCCW or some other internet service provider. And then these providers also connect with each other, such that when you send a message, if you want to, like for example from your house here, if you want to send something to Amazon, then it will go through different computers in between, right? And also some network devices in between before it can reach Amazon.com, right? And then when Amazon.com is going to send something back to you, like send back the product's information, it will also send it back through the internet and also through the different internet service providers and their network devices. Now we are going to talk about an example of how people have been using the internet using Netflix. So many of us are Netflix users, right? You maybe have been watching a lot of videos or movies or TVs on Netflix or other websites in the past few months. So we'll see how Netflix are actually using cloud computing, also through Amazon. Amazon actually is providing a lot of web services. So we know like Amazon started at an e-commerce company 20 some years ago, and then later on it started to sell many other things besides books, right? And in recent years it's actually also a IT giant, so it's actually selling a lot of IT services like web services. So So Netflix originally had their own has their own IT, but in recent years they also moved their computing to Amazon. Right? So that means instead of maintaining their own servers, as they are using AWS, the Amazon Web Services, to provide many of their IT services to their users. And so Amazon Web Services have their server farms. So these are like their computer centers where they have like thousands of computer servers to provide IT services. And they also have like redundancy. That means for the same movie, for example, it's not stored on just one computer, it's stored on multiple computers, such that when one server is not working, users will still be able to download the movie from another server. And also by doing this, a lot of times companies are trying to rent servers from these web services, right? So they don't need to have long-term contracts with these companies. And also, as we said, they don't need to maintain their own servers and their computing resources, which usually is quite expensive. So when a customer order a movie or try to get a movie from Netflix, actually, as I said, they may not be getting it from Netflix IT structure directly. They're actually getting it from AWS, from the Amazon Web Services server. Right? So Amazon is handling all this. And then what Netflix has to do is to basically of course load all their movies onto their servers on AWS, and also to have the programs, the logic with their user data and so on. When the customer ordering data, then they have to look at it on, they have to take care of them on the servers, and also they can get the viewing patterns and also analyze their customers' viewing patterns, and also do data mining to understand what their customers prefer to watch. So of course, all these would not be possible without the internet, right? Without fast computing speed. So when we talk about uploading the movies to Amazon Web Services, so it may not be uploaded by Netflix directly. It can also be uploaded by the other video content providers. And again, by doing this, Netflix actually saved themselves a lot of trouble of organizing and maintaining all these servers and IT services, and also making sure that the servers are working, because all this will be taken care of by Amazon. So when we talk about servers, so this one is kind of like the figures or diagram showing how the servers look like. So in general, you have something like what we call equipment rack. Then you can put servers here, or what we call the rack servers, and then individual rack server looks like this. So they don't look like your personal computers. So this one is a real picture. So this one is like a rack here. So we have multiple racks here, and then like each of them is kind of like a web server, and of course some of them are bigger, some of them are smaller, and then you can see all these colors are the cables connecting the servers to the network or to the other computers. Then the servers have different size. So this is thicker one is what we call 2U server, and this one is 1U server. So it's actually specifying the height of a server, like 1U, 2U, and the width basically is fixed. And then some of them can be like half rack. So this one is like 4U half rack. So in cloud computing, we know we have something called server virtualization. So when you have 4 physical servers in racks, like traditionally a server was basically a single physical server, right? But then nowadays what we can do is we can run virtual machines. So one physical server can run several virtual machines, and then each acts as a server. So basically you have one server, but then you have different portion of your computer running, it can be running different OS, and then they can also serve different users. So you can have virtual machines or virtual server running on one physical server. So virtual machines can be moved easily to other physical servers. So in that case, a virtual machine and the data is moved together as a single file. So it's actually making all this very flexible. So that's why when you are using Google Web Services or Amazon Web Services, you can easily like run different settings or different virtual servers on these computers or using these services. So new instances of virtual machine can be created in seconds via self-service tools. So you can create a virtual machine easily again when you are using GWS or AWS or similar services. And also more virtual machines can be added easily. So cloud service providers basically work like this. So when they are running their corporate data center or their server farm, then when the customer is connecting to these servers, they have to go through the basically what we call the network cloud. So basically going it through the internet. Right? Otherwise you will not be able to get the data from there. And so that's why again what we're trying to bring out here is networking is very important here. Is making all these cloud computing web services possible because of the much improved speed of the internet in the past few years. A customer can connect to various cloud services through the internet. Like for example, the Amazon Infrastructure as a Service, what we call IaaS cloud service provider. You can also connect to corporate data center. The user can also connect to like various Google applications. Nowadays, many of these services or software are actually running on the cloud. That means you do not have to install, for example, Gmail or Google Worksheets on your computer. All these software are actually running on the cloud. So that's what we call software as a service, SaaS. In the previous slides, we have different examples of cloud computing, like corporate data centers, infrastructure as a service, and software as a service. So this table compares them. So when you have corporate data center, the server is basically owned by the user or the organization themselves, and also the applications are also owned by themselves. So you run your own data center, you maintain your own hardware and software services there. And then when you run infrastructure as a service, basically the owner of the servers will be the cloud service provider. So it will be Amazon or Google or some other IT companies. And then you own your own applications. So you basically you run the infrastructure, but then you still run your own programs on those servers. And then software as a services, like everything is owned by the cloud service provider. Again, like Google Spreadsheet is a very good example, like Google Doc and so on. So they will be running the software on their own, and then what you do is you use it as a server. You use it as a basically a user. So you connect to the service, and then you run their software, and then you just load your data there. But still, all these services and also the hardware are owned by the cloud service provider. So traditionally, the organization owned and operated its own servers and application programs. The organization basically bought this hardware and software, and then they need to hire IT staff to do maintenance of this hardware and software. So this is what we call like infrastructure and software as a product. So you buy it and then you have to take care of it yourself. So again, in recent years, many IT companies are providing cloud services like Amazon and Google. So that means there is no purchase for servers, applications, or both. So you just pay by the amount of use, like electrical service. So if you use more, you pay more based on the internet transfer or the hard disk that you are using or the computing power that you are using. So this is what we call the infrastructure and software as a service. So of course, as we have emphasized, when you are using all these, the network speed is important. If you don't have good network speed, then all this cloud computing will not be possible. So when we talk about the internet speed, so we can think about the application download times. You want to download an email message of like around 250 words. Now, of course, when you are using a very slow connection, like 100 kilobit per second, like this kbps is kilobit per second. Right? Bit is just one bit, like 0 or 1. So 100 kilobit per second, then you can download an email message very quickly, but then you need to download a photograph of 2 megabytes. It may take 3 minutes. If you want to download a 1 hour high definition program, then it will take 3 days. Right? If you want to back up 500 gigabytes of hard drive, then it will take 16 years. Right? So basically that's impractical. So if your speed is improved by 10 times, now all this will improve, like 1 megabit per second. The nowadays standard is still very slow, but think about it, like when I was using the internet for the first time, like at home, some of you might have heard of like what we call the 56K modem. And most people use that around 25 years ago, 20 to 25 years ago, right? When people use a modem, that will make a strange noise when you try to connect to the internet through the telephone line. And when you are using that for internet download, no one else could use the phone. And so at that time, if I wanted to download a photograph from my email, like that someone sent to me to my computer, it would take like a few minutes. Right? So I have to carefully choose which photos to download and which photos not to. Because nowadays we are getting much faster. And normally, like in Hong Kong at home, we have the broadband, right? The basic connection is 100 megabit per second. But then of course we know in some areas, like for example, if you live in a relatively rural area, say in Sai Kung or some other places where the internet coverage is not that good, then your landline actually may not be up to 100 megabit per second, maybe just 8 megabit per second and so on. Of course, nowadays, if you are using mobile phone, we know mobile phone can also be very fast, right? And you have the 4G connection, you have like sometimes like 21 megabit per second or even faster. And also in recent years, we know we have optic fiber, right? Optic fiber even going to your residential units. So even for home services, Hong Kong broadband and also PCCW navigator, right? They can have like services like up to 1 gigabit per second, 1 Gbps. Now, of course, all these email photographs can be downloaded very quickly. And even if you want to back up a hard drive of 500 gigabytes or even bigger, then actually it will not take you too long. So all this become practical. So this table is just showing some meaning of these units, like kilobit per second, so that means 1000 bit per second. Right, so these are just some examples, like 33 kbps is 33,000 bps, right? And then mbps is megabit per second. And Gbps is gigabit per second, and Tbps is terabits per second, is basically 1000 gigabit per second. So of course, if you want to achieve a speed like this, like even optic fiber alone may not be fast enough. You may need better optic fiber or multiple optic fibers working together. So later on, when we talk about the networking cables in later chapters, then we'll talk more about this. In this subsection, we'll talk about an important concept used in networking that is called messages. Going back to our example of web browsing, when someone is trying to browse a website, then what happens is we'll follow the HTTP request and response cycle. So the client, so the user who is browsing the web, using the browser application, then when you type in an URL, this URL actually will be converted into an HTTP request message, and this message will be sent to the server address through the internet. So for example, if I want to retrieve something from IBM.com, then your browser will turn this request into an HTTP request message, and then you will also look up the IP address of IBM.com and then try to send this message to that IP address through the internet. So if the message successfully arrived at IBM server, then the web server will try to retrieve the web page requested by the user from the server, and then you will take the content. For example, it's an HTML page, you will package it into an HTTP response message, and then this whole message will be sent back to the client through the internet. So many of the internet-based services are actually based on message. When we have a long message like an HTML message or HTML request or response, especially like a response, it can be a large image file or a large HTML page. What we usually will do is we will have to break it down into smaller segments, and these smaller segments will be sent individually. When we break the long application message into smaller segments, we call this process fragmentation. So after doing the fragmentation, the application message will be broken down into smaller segments. So it will be done by your network software. And then these smaller segments will be packaged into something called frame or packets. So these are segments plus some header information. So one analogy I usually use is like you have some data, but you have some kind of like documents. So there are many pages, and then you split them into different smaller parts. So you have 10 pages per group. And then when you have the 10 pages, you put each group into an envelope. So and then on each envelope you write the address. So that's what we call the header information. So you have some information that you write on the envelope about where you are going to send this to, and also what is contained inside this envelope, that is this segment, and so on. So that's the header information. And then you send the data through the network. So you send all the different individual packets through to your destination through the network. One advantage of fragmentation is on error correction. If you do not do any fragmentation, that means you try to send your whole application message as a whole. Then if there is any error that occurred during your transmission, then you have to resend the whole message. So that may be very time consuming if your message is very large. However, if you have fragmentation on your messages, then when you are sending the different segments, if there is one error on one of the segments, then you only need to retransmit a single segment. So it will be much faster. Another advantage of fragmentation is on multiplexing. For example, like now host A wants to send something to host C, and host B wants to send something to host D. And then they may be sharing this network line. So when host A is sending some segments, host A may not be using the whole network capacity. So there is some unused capacity. So when host B is also trying to send something to host D at the same time, Then if you are doing fragmentation, then they basically can share the transmission line. By sharing the transmission lines, messages only have to pay for part of the total cost. So it's kind of just like when you have your broadband connected to your home. You are not using all the connection from your home to the internet service provider all the time, right? The line going from the service provider to your home actually is shared by many users. And supposedly not all users will be using the internet at the full capacity at the same time. So that's why again, when you are doing fragmentation, you can share the network usage much more easily. As we mentioned earlier, devices on the internet use IP addresses to uniquely identify their location. So then actually the internet is a collection of multiple small networks, like many single networks. And these single networks actually may be using different standards. For example, some of them would be a network running mostly on Wi-Fi. Like for example, your home network, then the router, and then your phone, your tablet, and your laptop computer together, they form a small network. And then when you are talking about this small single network, they may be using different standards and they use different types of addresses. A common type of single network address is what we call the EUI48 address. So when we talk about EUI48 address, many of you might not think this is something familiar. But what happens if I tell you is MAC address, right? MAC, MAC address. Then probably many of you have seen that before. So it's just an other name of that. It's a kind of like a more formal name of the MAC address. So the MAC address is 48 bits long. So it's used in Ethernet 802.3, Wi-Fi 802.11, and also Bluetooth. So it's used in all the common network standards. So Ethernet basically is the LAN cable. Of course, we know Wi-Fi. So many of the common single network standards are using these EUI48 address. However, we should note that not all single network addresses are EUI48 addresses. So as we said, formally it's called a MAC address. Actually, we still call it a MAC address most of the time. So it's written as a 6 pairs of number or letter symbols separated by dashes. So an example would be something like this. And then each of them actually has a decimal number. So A actually that means 10, right? B means 11, C means 12, and so on. And then F means 15, right? So each character here actually represents a number from 0 to 15. And actually when it is from 0 to 15, that means it's actually representing 4 bits, right? From 0000 to 1111, which actually means 15 in decimal number. So we'll talk more about these addresses and how we use them later on. So in the next few slides, we'll talk about some examples of single networks and some of the protocols that they use. So the simplest single network is a point-to-point network. So basically, you just have two computers connected to each other, or sometimes they may not be computers, basically just two devices. Or in networking terms, sometimes we just call them two hosts. So you just try to send a message from one device to another device. So then one thing that we need to have for the connection is, of course, the physical connection. So how these two computers or hosts are linked to each other. Are they linked using a fixed cable or using Wi-Fi or using other wireless protocol? So that's kind of the physical connection. We call it the physical layer link. So what is your transmission media and also what are the connectors? So when, for example, if you connect them through a LAN cable, then what are the connectors that you are going to use on the two sides? Right? Are they like how do the plugs look like? And also when you have this cable connector, how do you define the signal? What is the meaning of 1 and what is the meaning of 0? Alright, so you have to define these based on your standards. And then another layer that we need to look at above the physical layer is what we call the data link layer, or DLL link. So it's actually talking about the frame organization. That means when you send a message, how this message should be packed. Right. How you define the header for this message. When you send a message, what should you do? Do you need to say hello before you send the message? Right. So you have to actually define all these things when you are trying to have a standard for all these message between two devices on a single network. So PPP, point-to-point protocol, is a common standard that is used by this point-to-point single network. In computer networking, we have different layers of standards. So often the standards are created in layers, with each layer supporting the next higher layer. For example, if you are driving a car, then the soil layer supports the road layer. The road layer supports the tire layer supports the body layer, and so on. So what it means is that when you are trying to, for example, pave a road, then the road only need to know how the tires are going to work. So it's actually going to support the tire, but it does not need to worry about the car's body or the driver. Right? So each layer is supporting the next higher layer. So and also is going to interact with the layer below it, immediately below it. But in theory, it does not need to worry too much about the other layers that are not immediately above or below itself. But of course, in practice, sometimes you still need to think about the other layers. But then at least in theory, you just do it layer by layer. Then you can define the different standards at the different layers more clearly. So when you do layering, you actually can do better specialization. For example, the road engineers do not have to understand tire standards or body standards in detail. So when we talk about networking, it's again like the one who are designing the physical layer, right? When they are designing the cables for example, LAN cable for Ethernet, they do not need to worry about what you are doing with it, what kind of applications, whether you are using it for Facebook or Gmail or other applications, right? They don't need to worry about that. They only need to know that I can transmit the data physically, and also is supporting the layer immediately above it. I need to support the standard message transmission at the data link layer, but I actually do not need to worry about the layers that are further above me. So that's why you can focus on what you are doing, focus on the physical transmission without worrying about the other layers. So we have talked about the physical layer standards. So the physical connection between the adjacent devices in the network is a physical layer. So that's kind of like the again, the LAN cable, the Wi-Fi signals, and so on. So the physical layer governs the transmission media and the connectors. So what connectors you are using, and also what you should use to make the cables, and so on. So you're also governing signaling to transmit ones and zeros. Again, when you are transmitting the data through a physical cable, then what is the meaning of one? Or how you represent one. So is it so you have to define, so is it going to be a voltage higher than a particular threshold, then it is a 1. If it is a voltage below a particular signal, then it is a 0. Right? And then you also need to define what is the length of each signal. And also if you are doing Wi-Fi, then of course again, what are the ones and zeros that are being or how you are going to represent the ones and zeros using your Wi-Fi signal, the electromagnetic waves, right? So that's kind of what we call the physical layer. And physical layer is the bottom layer in the in computer networking. So usually we call it the layer 1 standards. And then data link layer is the second layer. So actually the end-to-end path of a frame between the source and the destination host. So a frame is basically a message at the data link layer. So it covers the frame organization. It also covers how forwarding devices like access points or switches forward frames over multiple hops. So in the data link layer, we are dealing with the messages within a single network. But even within a single network, you may have multiple computers, multiple devices. So the data link layer actually defines when you want to send a message, or in this case, what we call a frame, from one host to another host in a single network, then what path it should take to send the message, how it's going to forward the message to the next device. So it also covers the data link layer address, or what we call the DLL addresses. So it's usually called the layer 2 standard. So as we said, point-to-point protocol is the dominant data link layer standard for point-to-point networks. And then this one is an example of an H2O.11 wireless single network. So H2O.11 basically is Wi-Fi, right? So we have been using it every day. So you have your Wi-Fi client, so it can be a tablet computer. Then it's actually sending messages to the wireless access point, right? And then it actually may be also connected to a Wi-Fi wireless server host. So when you are sending a message from again this client host to the server host, then again the wireless access point has to know how to forward your message, right? If you put an address there, then what is the meaning of this address? What is the size of the frame that you can send? You know, and so on. So all these will be defined by the protocol, right? So like of your data link layer. And then this one is another example showing kind of a wired network with many switches and also some computers connected. So this is very common for like for networks, say within an organization, say within Hong Kong Youth, and we have like many different devices connected to each other, right? And then each switch may be connected to other switch. So a switch is a device that actually can kind of decide how your message should go, right? When the switch receive a message, then you will decide where I should send it next. So if you have a network like this, then all these physical cables, so again you may have LAN cables connecting all these computers and switches together. So this is what is defined by the physical layer or physical link standard. So how thick your cable should be, like what should your cable should be made of, and what connectors you should use. And of course, like these are all defined based on the standards. And then you have to, of course, you don't make the cables yourself like normally. Then you buy the cables, and then you can link the computers together. But at least like you have to follow these standards, right? The products have to follow the standards. And then when you really want to send a message from, say, from host X to host Y, then from host X, then I need to package the message into a frame. So I need to put it into an envelope, right? As we said, kind of an analogy, I put it into an envelope. But then this envelope has to be of the correct size. And then what I write on the envelope should also be following a specific standard. So that means the header that you are using should be following a standard specified by the data link layer. Right. So and the data link standard will decide how your message should go, like whether, like if switch A receives the message, whether it should send to switch B or C. Then these are defined by the data link standard. So in networking terms, sometimes we also call this, like when you have this link between two computers, so we call it the physical link. So these are physical links. So this was one link, this was another physical link, this was another physical link. And then when we are talking about the path between X and Y here, we call it the data link. So this is the actual path that will be taken by your message. Then we call it a data link. Right, so sometimes again in networking terms, when we are talking about the path from X to Y, like following what we have on this figure, we will say there's one data link in this path. And then there are like 1, 2, 3, 4, 5. There are 5 physical links here that are involved in this path from X to Y. Many single networks are what we call switched networks. So that means there are many network devices which are called switch that will help the functioning of these networks. So for example, source host X wants to send a message for destination host Y. So first it will send a message to the switch that is connected to, so it will send to switch A. Then what must switch A decide to do next? So you have to decide whether I forward the message to B or C. So switch A will make the switching decision on the basis of the switching table. So you will have a switching table like this. So what it is saying, if the destination is Q, then the next switch, or what we call the next hop, will be C. If it's sending to W, the next one will be C. If it's going to X, then the next one it will be X because it's connected there, right? If the next host will be Y, then I know I should send it to B. So I actually just follow the table. So later on in later chapters, we will talk about how the switches actually come up with this table. But now you can just suppose the table is already given. So you will forward the packet address to host Y to switch B instead of to switch C based on the table. So switches only know the next switch, but not the frame's entire path through the network. So again, when switch A receives the message, I know if it's going to Y, then I should just forward it to B. But I do not know whether it will go to D or E or anywhere else after it goes to B. I only know I just pass it to B. Then it's not my business anymore. So again, then what decision must switch B make? How will we make it? So switch B, as we said, it will have to decide whether the message should go to D or E, and it will make the decision based on its own switching table. So some networks are what we call the hybrid switched or wireless network. So here we have an example like this. So you may have a network like this. You have a server needed by the client, and then you connect to it's connected to an Ethernet switch, so a switch device, and then the switch is also connected to a router that you can use it for internet access. So it's connected to the internet. So later on we'll talk more about what exactly are these different devices like router and access point and so on. But for now, we just look at the example first, and when we go to the respective chapters, we'll talk about each of these in more detail. And suppose you have a client using the laptop computer, and then it's connecting to the access point through radio transmission. So in this case, it's most likely Wi-Fi. And then the access point is connected to the switch through UTP, is basically the what we call the unshielded twisted pair. So basically in the meantime, just treat them as the LAN cable. So your Ethernet or LAN cable that is connected to the switch. So you can see this switch actually is very important. It's actually linking all the different things together. The router, the router here that will allow, say for example, the client to connect to the internet, right? And then the server that may be needed by the client. As you say, you have some, as we said, there are some data there that can be accessed by the client. But then at the same time, it also has the wireless transmission here. So this is an example of what we call a hybrid network. So when you are using it at for example, if you imagine your network at your home, right? Actually, many of these router will also be your wireless access point, because if you think about it, like in many of the home setting, what you have is you have your internet connection coming into your home through the network jack or sometimes through a modem, and then what you do is you connect your modem or your you basically plug your connection into what we call a wireless router. So a wireless router actually is a combination, is a combined device of a router and access point, right? So the router is the one that will allow you to go to the internet, like from your home, from your laptop computer to the router. That's your home network, your single network within your home. And then the router actually will go to the ISP, right? So the router will allow you to connect to the internet, right? So that's that's kind of like what we have in this diagram. The router is kind of the link between this single network and also the internet. But what is different from this diagram from kind of a simple home setting is that normally, as we said, the wireless access point and the router is the same device. That means when you are using a laptop computer, you don't have a switch at home, right? You just connect to the router, and then so the router actually is also the access point, and then it will allow you to connect to the internet. Actually, another interesting thing that I did not mention is your router is actually also like a switch, right? Because many of the router, you also have some LAN cable that you can plug in, right? So you can have several other computers that you can plug into your wireless router at home, right? Like through kind of some of the plug on the back panel, right? So that's why in a simple network setting at home, right, you have all these three devices, a switch, a router, and an access point in one device, right? Usually we call it a wireless router. But if you are talking about a larger setting, for example, like a campus setting in a university, then all these devices will be separate devices. In this session, we are going to talk about how single networks can connect with each other to form internet. So there are some problems for connecting hosts on different single networks. Of course, like different networks can be running different standards. So if they're running different standards, they actually cannot talk to each other. And even if the two networks follow the same standard, a host on one network may actually have the same DLL address as a host at the other network. So there can be overlapping addresses, and then when that happens, then there will be ambiguity, and the network devices will be very confused, right? And if the link use the standard of one network, then it will not connect to the other network for the first two reasons, right? So basically, it's difficult or basically impossible for hosts on different networks to talk to each other. So that's why people came up with the idea of inner networking with what they call a router. So the router acts as the destination host on network 1 like this, right? So for example, this is a single network 1, and then host A is trying to send something to host B, which is on another network. So this frame will be sent from host A to a device called the router. So nowadays, when we talk about router, many of us will think about wireless router, right? The thing that you basically enable Wi-Fi at home. But actually, the router is more about the connection between different networks. The wireless part is because the router also have the wireless access point, as we mentioned earlier. So after the router receives the message from host A, it will also act as the source host on network 2, like this. So this is the second network. So what it will do is that it will take the message, the frame 1, remember in the previous slide, the frame 1 from host A. I will take it, and then I will have to take care of the conversion. So I have to make sure it's something that is following the standard of network 2. So I convert the message in frame 1 into the message into another format, with other packaging and so on. So now it's like frame 2. And then frame 2 is something that I can transmit on the single network 2. So then I can transmit it to host B. So we can think about it like this: single network 1 is like a place where, for example, it only understands English. And then single network 2 is somewhere that people only understand Chinese, right? So when host A is sending the message to the router, is actually writing an English address on the envelope. So after it arrives at the router actually has to take the message out of the envelope. So throw away the envelope. And I need to put the data into another envelope. So that is the header of frame 2. I put it into another envelope. I write the Chinese address on the envelope that is understood by the post office in network 2, right? Then I can send the message successfully to host B on this network using the protocol of this network. So that's kind of the basic idea of how router can be used for connecting two different networks that may be running two different standards. So the IP packet and the data link layer frame are actually having relationship like this, right? So in the single network 1, so we have this frame 1. Single network 2, then we have frame 2. So this is kind of like the envelope that I talked about for the frame. So the source host creates the packet. The host places the packet in frame 1, and then the host transmits frame 1 to the router. Right. So the packet here actually is the header information for the internet layer. So you can think about it as another envelope. So I first put in one envelope with the IP address. So we have the internet address. And then I put it into another envelope with the network header of network 1. So it's sent to the router. And then when the router receives that frame 1, so the router takes the packet out of frame 1. So again, it will take out the packet out of this frame 1 header, right? And then the header of frame 1 will be thrown away because I don't need that anymore. And then the router will have to place the packet in frame 2 format. And then it will send the frame over the single network 2 to the destination host. So you will follow the process here. You see the packet is always unchanged. It's just put into different envelopes. So that's why when the message is sent from host A to host B, the packet is still the same. And then after host B get the message, it can take out the packet header and then get the actual data from there. So we have seen the encapsulation of network messages, and then we know there can be multiple levels of encapsulation. So the idea of encapsulation is basically like putting the message into an envelope, right? Just the analogy that I use. And then you can also think about it as like adding some header information to your message. So traditionally, you may put a frame like this. You have your application message segment, and then you add a frame header. You add some header information. So it becomes a message that is encapsulated as a frame. But when you transfer a frame on the internet, because we need to store data like with the IP address, right? If you only have frame header, you only have the address within the single network. But then I also need to have the internet address. So that's why I also have the IP packet header. So when you want to send a message, remember first we break it down into smaller segments, and for each segment, then we add the IP header. And then after adding the IP header, then we further add the frame header, right, within your single network. So you can see the IP header actually does not change, right, no matter which network you are at. But then the frame header will change when you are sending it through different networks. So and then also for some terminologies for this part, the application message plus the IP header, we call it the IP packet. But then when you also add the frame together, the frame header together, we call it the frame. So in other words, both frames and packets are terms for messages that have been encapsulated. So again, for terminology, usually at this IP level, we call it a packet. At the data link level, we call it a frame. So we just kind of have to remember that. So this one is an example of a relatively more complex network where you have two single network or switched network here, X and Z, right? And so if host A want to send a message to this host B here, so it has to go through different switches, and then it will go to this router R1, which is the router within this network X, right? And then this router will have to kind of extract the packet from the frame, right? Originally we set as a packet in frame X, and then I will have to take away the frame header, right? Because I don't need that anymore. And then I need to package the packet into a new frame, like based on the standard used in this connection. That is the connection between router 1 and router 2. So it's actually another single network here. So after router 2 receives the message, router 2 actually also need to remove the header of frame right. So I take out the packet and I put it into frame C, based on the standard of network set here. So after putting it into this frame, then I can send it within this network set, and then I can send it to host B. Right. So that's kind of how this network works, right? When you are trying to send a message. So here are some of the again repeated concepts at the data link and the internet layers. So just a table to summarize this. At the data link layer, we usually call it layer 2, and the internet layer is layer 3. So we call it the data link layer and also the internet layer respectively. And there are many different standards at the data link layer because you can have different types of single networks. They can be wired or wireless. Like they can be Ethernet, AO 2.3. So that is kind of the standard wired network using LAN cable and so on. And then you can have Wi-Fi, and also you have different versions of Wi-Fi, right? And then you can also have point-to-point protocol and so on. So there are many different standards. But at the internet layer, there is only one standard, is the IP standard, right? Internet networking protocol, so IP. And for the addresses, so they are at data link layer, they are called the data link layer addresses. So they are often the EUI40 addresses, but sometimes it can be other addresses. At the internet layer, it must be the IP addresses. Although there are also different versions of IP addresses, like IP version 4, which is kind of the old traditional address, and also now we have the IP version 6, which is the new version of the IP address. They have been around, actually they have been around for quite a number of years too. And as we mentioned, the way that messages are called are different at the two layers. When we are talking about frames, it's always at layer 2. When we talk about packets, that is at layer 3. Then the forwarding networking devices are called switches and access points and so on. And at the layer 3, then they are called routers. And the paths at layer 2 is called data links. And at layer 3 is called routes or routes. The process of fragmentation and also placing a message in an envelope is generically called packet switching, which is a rather common term in networking. So some of you might have heard of that. However, as we have seen in the previous slides, packets are routed and frames are switched in the second layer. Packets are routed in the third layer. So technically speaking, packets are never switched. So we should call it packet routing or frame switching. But somehow, like this term, packet switching has become quite common. So people have been using it. Okay, so in the last few slides of this chapter, we are going to talk a little bit more about the different standards layers. We have talked about three network layers, like the physical layer, the data link layer, and also the internet layer. So in the TCP/IP model, or sometimes we call it the IETF model, usually there are 5 general standards layer. So layer 4 is the transport layer, layer 5 is the application layer. So this is also the model used in our textbook. So in some other textbooks or some other models that you will see, some networking standard that people use is what we call the ISO OSI model, where ISO is the International Standards Organization and OSI is the Open System Interconnection. So basically people call it the ISO OSI or ISO OC, right? So basically that one has 7 layers. So in general, it's kind of roughly like the first 4 layers are quite similar across the two models. But then for the ISO OSI model, the layers 5, 6, 7 are kind of similar to the layer 5 here, the application layer in the table that we see here. So let's focus on this model first. So the highest level, layer 5, is the application layer, which actually standardizes the communication between two application programs of a certain type. For example, if we are talking about the World Wide Web, then it will be actually the protocols for web server and web browser, and also the HTTP message and the HTTP request and response. So this is the protocol for one application, and there are many different standards, right? Because there are so many different possible applications on the internet, right? So that's the layer 5. And layer 4 is what we call the transport layer. So it's actually handling the fragmentation and other functions of your messages. So the most notable example is the TCP protocol, and also another one is the UDP protocol. So we will talk about this in more details in later chapters. And then we have talked about the internet layer, layer 3. So it's about how we transmit the packet across an internet. So packet organization, router operation, other things needed to transmit the packet across a route in the internet are defined in this layer. Layer 2 is data link layer. As we talked about, is actually about transmitting a frame across a single network. So frame organization, switch and access point operation, for example, how we come up with the switching table, and also other things needed to transmit the frame across a data link in a single network are defined at this layer. Then again, the bottom layer is the physical layer. It's really about the transmission media, plugs and connectors, signals, and so on. So there are different networking standards, agencies, and architectures that we said the two major ones are the OSI model and also the TCP/IP model. So the OSI model is governed by the ISO and the ITU-T. And then the TCP/IP basically is handled by the Internet Engineering Task Force. So architecture naming is called the OSI model, and this one is generally referred to as the TCP/IP model. And they actually come up with different standards that people follow, and at different layers, actually some people one of the two agencies actually may be sometimes more dominant, right? For example, OSI actually they dominant at the physical layer and the data link layer. So basically they come up with a lot of standards in these two layers, like the optical fiber, Wi-Fi, and the Ethernet. And then TCP/IP are mostly setting up the standards at layer 3 and layer 4. Right, so internet layer, transport layer. So TCP/IP, domain name services. So these are the standards kind of proposed and kind of maintained by TCP/IP or the Internet Engineering Task Force. So in the last few slides of this chapter, we'll talk a little bit more about the domain name service or domain name system that we just mentioned. So when I try to send a message from one computer to another computer on the internet, so a lot of times I don't memorize the IP address, right? I only have the domain name like IBM.com or Google.com and Yahoo.com and so on. So suppose in this example, I want to send a packet to this domain called the voyager.schindler.hawaii.edu. So first I need to find this IP address before I can send packets to this IP address. So I need to find the IP address. So I do it through a domain name system. So I will send a DNS request message to the DNS host. So I want to get the IP address of this host. And the DNS host will look up it in the table. And if it doesn't know the answer, it will ask other DNS servers. And then after finding the answer, it will send a message back to me saying the IP address of this host is this and this. And it, as we said, it looks up the address from a DNS table, right? And then it will send the response. And then after getting the response, so now the originating host knows the IP address of where I want to send it to. Then I can put this IP address in the header of my packet, and then I can send it to my target. So that's kind of a brief introduction of the DNS. Okay, so and also this is the end of this chapter. So just a quick recap. We have given introduction of cloud services, also talk about the importance of the internet, and then we talk about the 5 layers architecture in the TCP/IP model, and then in particular talk a little bit more about layer 2 and layer 3, so how the data link layer and the internet layer work. And then that's kind of what we cover in this chapter, and then in the later chapters we'll talk about these different topics in more details.